Let me start with some hype. By now, you must be aware of artificial intelligence. You must be aware of ChatGPT, maybe DALL-E, maybe other language models, Bard for Google, Gemini is a new thing for DeepMind. Every major player, every major piece of industry in technology is attempting to create language models which do a lot of the things which humans do, but we thought computers couldn't. But it's more than that. The hype around AI is not just the fact that our computers can do what we can, but actually AI can also now do things which humans can't. This is some of the things that often gets overlooked when we're impressed by your language model, being able to talk to you about the weather or ask it about what you should do in aspirin. Actually, there's a whole other part of the AI revolution, which is enabling scientific achievement to go way beyond what we could ever do as humans. And a good example of this is a whole new area of biology where we have the huge complexity of how DNA works and how we can control organisms, both pharmacology, for medicine in general, or a whole host of other industrial things. We can now open that up by understanding the language of DNA. It's AI that's enabling. Apart from language models you're used to, the hidden industrial parts like this, there is also growth in the academic work which signals that we are in the presence of this sort of revolution. So this is a plot of just the number of papers, the number of academic works in different fields from 2010 onwards till now. And the three at the bottom are what I would call traditional subjects: high energy physics, mathematics, other areas of physics. And this orange one, the orange one that's taking over, computer science, and in particular, AI. And you can see it starts out just 10 years ago in traditional sciences. It's now taking off with a sort of exponential growth, as this is the field which has attracted the young people, where the new ideas are, that we are getting a whole new way of looking at how these things work. So now I provided you with the hype, as if you weren't already hyped up about artificial intelligence. Let me come to what we're going to talk about this evening. So the background is in theoretical physics. I like to approach things from the most simple point of view possible and build upwards. So we're not going to get all the way to ChatGPT. What we're going to do is go back and understand the origin of many of the ideas that underpin all of AI today. So where do the ideas how to do AI come from? How do you use insights from the sciences that we've had for years to build artificial intelligence? We're going to begin with the history of AI. Of course, the most obvious thing, which is that if you want to be intelligent, you better have a brain. And so we will look about how the brain provided the first model of artificial intelligence and what that means. And then, perhaps more surprising, how many of the ideas in physics came and got used as tools in AI. And I will end with a discussion about the future. That's always my favorite part, because at this point, it can't be wrong. So, brain. What we're witnessing here is brain growing connection between neurons, which are like the big blobs, and the dendrites go out, and they will connect to other bits. And this is how things like memories are formed, and this is how the brain grows structure that allow us to have thoughts. So first of all, I find this a remarkable video. The fact that we can see brains growing their connections is already remarkable. But what you get from this is that how brains work is by having a network of things that fire. And you can see things firing, they're the neurons, and then what makes them fire input from being connected to other neurons. Okay. So this has been known for a while, this sort of ability to image it from recent technology. So our brains, these networks of neurons connected together, not necessarily each to each, but then they respond in different ways to stimulus. So what happened? People understood to some extent, or at least inspired by, that our brains work through having a network of neurons that fire. Those firing neurons can lead to your hand moving or some thoughts. And those get triggered on input stimulus, whether it be through touch or things that I see. Then there is some very complicated network in between that allows it to express control, say a muscle, or our understanding of ideas. Okay. So then, taking that as a model, we sort of simplified it, made it more abstract, mathematically tractable. We produce these things called deep neural networks. So what you imagine is that you have some inputs. This could be an image or something else. And it's going to go, these are going to, when they get stimulated, so the input will be the on or off in some way. And then it'll be connected to all these different layers. But the strength of these connections will differ. And that will be what learning is. I'll come back to that in a minute. But then in the end, once it goes through this network, the output, which is deciding what it is that you see, will be at the final layer. Okay. So for biology, we got the idea that our brains worked as networks, firing things. We had some inputs that were firing, and outputs firing will tell us what thoughts are. And then we had this complicated network in between, which allowed the expressibility of our brains. How does this work? Let's look at an example. This is the number 7. It gets broken up into pixels. You can see it. There's our pixels. Each pixel goes into one of these things. Then, depending on the strength of those connections, it will set off the neurons in the next layer, and the neurons in the next layer, until it comes out with the final output neuron, and is what the class is. Are people happy with that? Great. So what this tells us is a remarkable thing. They've all kind of really complicated sets of numbers that we write down. It's not learnt them all, but it's finding common features that then allows it to classify and understand what's written. This is roughly what happens when you have handwriting recognition systems. So a crucial part of this, though, is the strength of these connections. Here, I've just shown you the network working, not told you how it's learnt what these connections are. So the next thing we've got to do is understand how we move to learn something and fix how these neurons are connected together to achieve this. Okay. So, how do we learn? So, learning is a very grandiose name for something that in artificial intelligence is actually quite simple. To learn something, first of all, we need some data. Okay. We don't learn in vacuum. I need a data set, I need things there, and the idea is I learn some connections, some underlying structure between the data that's there. So this could be a plot of, I don't know, number of people skiing in Aspen versus the visibility at Button. Not surprisingly, it goes up. But indeed, there may be other factors. There's some noise. Could be depends on whether airports have been recently closed, whether you can't drive from Denver, etc., etc. Okay, but the basic trend is there that the better the visibility, the more people. But we don't know that. We measure on various days the number of people who and we get these blue boxes. And then what you want to do for learning is the best line you can get the underlying trend that fits this data. Okay. Now, so this is a very old idea. And most humans would do this really, really simply. Give you those dots, ruler, and by eye, twiddle it, and you go, oh, yeah, that looks right. But what are you doing when you're twiddling it, going, that looks right? What you're doing is minimizing the distance to the line that you're choosing for all the data points. Okay? Now, that's fine, the line. We may have seasonal variation, very few people skiing, or whatever other factors there may be. So this might be the data set. And I would be completely stupid to just put a straight line through here. So I've got to say, no, you can all play this game. If you were given that set of points, what line would you put in? Here's a suggestion. It will go like this. Okay. And again, what you're trying to do is minimize the distance at each point from the line, while at the same time, not trying to go crazy and fit every line, because there might have been just some weird behavior on one. So this gives us the basic challenge of learning, which is finding an underlying trend behind the data that we're given, which is we can be really simple and then try and fit the data like this. And that looks not quite right. It looks like this, which should be much better. The trend that the data tells us is like this. Or this could be better, but that just looks like I'm a child and have played Doctor. I've not understood the trend. So learning is about finding this thing which captures the underlying truth, not doing this, which doesn't, not doing this, which basically just tries to go from data point to data point, and you have no real faith what's happening, say, here, because you don't really understand the trend. This, you understand the overall trend, so you know where you'd like to go next, and extrapolating beyond the data you've seen. So neural networks, and here I have put the technical phrase, whatever reason, tend to balance this over and underfitting challenge. And maybe that's why nature evolved the way it did, because it's a successful way to meet this challenge. And one of the issues that we have, indeed at this conference, is meeting here, is understanding this thing of how neural networks generalize and understand them. So far, learning looks easy. I've got some data. I've got to fit some way through it so I can extrapolate and understand and find the trends that are in the data that I give you. The problem is that I just showed you as one line, one dimension, not a very complicated situation. Now, when we have more complexity, we've got challenges. And in particular, I said we should put a line through it so that we minimize that distance between the data points. But if we're in many dimensions, it would be like putting some really complicated, very complicated line with very high dimensional thing. And it's really not clear how to do it. You can do it with your eye. You've got many pieces of data with lots of dimensions. But you can write down the maths. you can attempt to minimize that distance from your data to the trend that you've found. Here's the complexity issue. How do I find the best fit? Here already, the best fit here, this surface is meant to be showing all of the sum of the distance points from the data. Is you sort of go down a hill and end up in the bottom and you go, this point here is the point which most fits today. I'm worried I'm going to lose you in this bit. So what you should think of is I'm making choices how to get the underlying trend. What could happen is it's really hard to work out because of all the different ways I can change how curves fit. So mold ideas, basically finding the minimum of something, is to literally roll a ball down the surface, you'll find the minimum. Okay. So this is what Newton would do. If you want to find the minimum of a valley, roll a ball. Here it should be a sphere. And you'll end up in the bottom of the valley, and that will be your good choice of things because it'll be at the bottom. Now, the problem is there can be some surfaces, you've got a fake bottom of the valley, then you end up there, you've missed the better solution. Okay? And when you're here, you don't know that this isn't the true valley. Nobody gives you a map. You're just exploring stuff. But going downhill all the time, then you think, if I go downhill all the time, I'll end up in the bottom of the valley. But it's not true. If you start here, you end up there. So what do we do? Physicists face this problem all the time, all sorts of problems. They introduce randomness. And the reason we do that is because when you think you're going to get stuck at the bottom of the valley, if you've got some randomness, like temperature pulls you, some other effect, every so often you'll get a flip, and you'll start here and roll down. This was an idea that goes all the way back to simulated annealing. Those of you who don't know, annealing is a process people use to make better iron. It's a really simple idea. You heat up the iron, you keep it above a certain temperature, you cool it very slowly, and then when you do that, the iron that you're left over with is much stronger because it's found the true best configuration for it to be in. And it does so by this way. If I just make iron and cool it quickly, you put it in you see people on film who take iron and put it in a piece of water. It'll end up brittle because it will end up just stuck here as a crystal. And increase it by having randomness, we can find solutions better. So this is an example of simulated annealing. So the idea is, actually, I wanted to at the top here. It moves around according to something just jiggling at a temperature. You slowly lower the temperature, and you end up at the true top. This high temperature, it jiggles. Then you lower the temperature, it jiggles less. Eventually, it will find an absolute top. Okay. So this idea was an old idea from physics and became very useful for how we find all sorts of problems which are very complex in nature and require us to not be stuck in a way that we start off with. So this is also the traveling second problem. You've got to go from every node, and which order did you do it in? And you start off at high temperature and all different solutions, and you set it equal 0, the low temperature, you end up the best solution. It shows you how. It shows you higher dimensions even, when the problem gets even harder. You slowly lower the temperature. There's a bit of a lag on this. Then you solve the problem. We had a bit of a glitch. Okay. So these are just some basic ideas about how we can learn. We don't get stuck in a rut of learning by introducing randomness. How else do people take ideas from physics and use it to create AI models? Well, Let's go back a few hundred years to the last revolution, in particular the Industrial Revolution. So the Industrial Revolution, people created engines, right? Steam engines, everything else, they powered industry. And we're in a situation very much like that now. People are making AI models. We've not completely got a full theory of it. During the Industrial Revolution, people realized they had to be able to understand the full complexity of something like an engine. They came up with the theory of thermodynamics. Now, thermodynamics, the area of physics, embraces randomness. Sometimes you're taught that physics is all deterministic. It's all very, you know what's going to happen next. Thermodynamics is all about the high-level view of a very complex system, multiple components, but you really can't know what will happen next to one piece of it. But instead, what you do is you introduce ideas like temperature, the thermal energy, and then this idea called entropy. Entropy measures information in systems. High entropy is low information, and low entropy is high. I'm going to give one really simple example of this. The air in this room is governed by the laws of thermodynamics. There are many molecules of air in this room. Very many. Trying to estimate it, but I won't. Beyond anything you could simulate on a computer now. They all bounce out off each other, and there's no point describing the location of each particle. But what you do want to know is if you're sat in this room, how hot it is. That's not to do with the energy of one particle. It's to do with the statistical distribution of all of the particles in the room. You do through one number, which is temperature. Okay. The entropy will tell us even more about the information of the distribution. So now there's very little information about particles in the room. It's spread everywhere. But imagine something else. Imagine if all the particles were up there in that corner, or it's not, you can still breathe. And, well, now, that's of all of the possible ways in which all the particles could be, that is very, very unlikely. That contains much more information. I've got to specify all the particles in a very unlikely place. Okay. And compare that to where they are spread out. I'm going to come back to that later, about the different notions of entropy and information. Okay. Now, the idea of entropy itself is used extensively in the development of quantum mechanics. It gives the whole idea of what we mean by information and so on. It makes sense that what we're learning is measured in terms of information. So this idea of entropy was introduced in thermodynamics is now the way as a theoretical tool to tell us how close our AI model is to the world, probabilistically. So I'm going to come back to how we can use this idea to imagine how we might do some learning. So diffusion, the process which you're sort of familiar with, if I start with all the gas up there, wait, all the gas molecules will bounce off each other and will end up in the room. So diffusion is a process where I move going from low entropy to high entropy. Okay? And that then is a flow where we go from something with lots of information to very little information. And indeed, one of the laws of thermodynamics is that entropy grows. Lose information in processes. The ultimate meaning of this is this idea can be used to flow the other way. If going from all of the gas up there and diffusing takes us from having high information to low information, if I can run it the other way, I can go having very little information in the system to generating something with lots of information in it. practically, I could never do it with a gas. I could not run around and then somehow get all the gas to go up there. And that's not something that we can do physically. We can consider the reverse process and say, what would the process be where I take the pure randomness of gas in this room, and then when it's all in the corner, I'll then have a real high information state that could then contain interesting things. Let's look at this, the cat. This and AI people like cats. Schrödinger likes cats. The ML community is obsessed with cats and dogs. And we'll start with a cat. And what we're going to do is do the process of diffusion going one way. So information in this picture, let me go the other way. This is a random picture. It is the equivalent of all of the gas and information. Just saying, take all of the pixels that you've got and pick a color and a random intensity. This is random noise. The cat picture is really unlikely from random. I just pick it randomly to just reach a cat picture. That's like monkeys on typewriters writing works of Shakespeare. Right? The equivalent that cat picture is like all of the gas molecules being up there, just randomly bouncing off each other. Yeah. Very unlikely. And that's why there's such information in this picture, because it's a very unlikely thing compared to noise. Now, what happens is you can say, right, let's diffuse this. Let's move from the cat picture and go through a diffusion process, like the gas molecules escaping from there to the rest of the room, and go down. Now we've got no information. We've achieved absolutely nothing. We've taken stuff with information, we've thrown it away. But now what we do is we ask the computer, through the learning algorithms that we've spoken about in terms of neural networks and optimization, to learn the process here to here, invert it. Why? Because it means any piece of noise here, which I invert, will produce a cat picture. Not necessarily the same cat, because it's like up there, all possible cat pictures. We have, and then let them diffuse out to the full room. But now I think the other way. I think start, imagine, bring it backwards, and then we end up with the cat picture, even a picture of a cat that has never been seen before, because in a space of pictures live compared to all of the possible randomness. So I realize this is a lot to take. But the thing that you should think of is that the ideas that came about in dynamics of how we go from randomness tends to be favored something a lot of information. Turning it around allows us to generate structured information. And that's the basics of generative AI. And indeed, that's what was used to create this picture. So what's remarkable is something that seems so simple, which is doing a diffusion process backwards and produce something as complex as this. So this, I think, was with Bali too. And the prompt I asked it for was Newton and Einstein talking with an AI. And it managed to produce this. What's remarkable for me is the process that it produced this started with random noise. And then what the computer learned is how you go from randomness to depending upon what you do. There's interesting little bits, by the way, like, why is Einstein wearing a necktie like Newton? Etc. And equally, when you ask ever about AI, it always tends to do a robot, which makes me think it's self-image. embodied, even though it's not got any body, but that's not what we about that. And the equations are completely wrong in geometry, which is really disappointing for a physicist. We've got Newton and Einstein meeting, the blackboard makes no sense. Come back to whether the blackboard should make sense. I think it's important to realize the inspiration. Given these examples of dynamics, physics of the 18th and 19th centuries, but now we can use ideas from quantum field theory, which is the fundamental approach we have to understanding to do even more sophisticated things. We can take ideas from condensed matter, the physics of things like magnets, and use processes that happen in nature, then give us models of how artificial intelligence. So I'll say a little bit more about those. I think the thing to realize, because you could ask, Dave, why are you going to physics hall? The first point would be, I have a bias as a physicist. Because we tend to want to use the language and the things that we've been brought up on to tackle any problem. But it's a little bit more than that. There is something deep about the way nature has structured itself that contains so many ideas. And often when we study nature, we think we're solving some particular problem, say the problem of magnetism. And then someone will, I don't know, they've used magnets for MRI scanners, magnetic storage. But in the end, so those very same ideas came around to a way of using artificial intelligence. But you would never stop and say, I'm going to come up with artificial intelligence and use theory of magnets. The reason why I'm emphasizing this is that sometimes people say, what use is fundamental physics? And so I'm going to say, you never know what use is, and it will often decide in studying 50 years' time. Okay. Now I've given the party line on what physics is good. It's not just about solving the problem now, it's about giving you the language to the future. Let me talk about a little bit the future of AI. So I said those equations on the blackboard were sort of wrong, nonsensical. It is much harder to make an AI do careful analytic thinking for this type of mathematician. I'm not saying it's impossible, but these sort of models rely on probability and statistics. It doesn't rely on saying, all of the space of things it can do, there is one solution which you carefully find. It says, what's the likely? When you write down equations, there's lots of things which look right to the AI, but just don't have meaning. And I think there's still some issue here. That things like language models are not very good at careful analytic thinking to the level which we believe, because they appear to be very human in capabilities. So I think the future begins with a warning about where we are at now. But this is literally tackled and what we'll be able to do potentially in the future. So I didn't really talk about planning and control problems, but indeed, the picture of AI as a robot is that it's not enough to exist in language, to exist in the world. You want your AI to help you do the shopping, change the nappies, empty the dishwasher. Or indeed, at some industrial scale, do whatever. Drive a car. This is still not yet complete to the same level we've achieved with things like GPT. There are certain things about planning and control have been emphasized by a lot of people in the community, people like Jan LeCun, that we've still got some steps to go, and we should get to carry away with GPT in this area. These two may be linked. The planning and careful analytic thinking will be cognitive. The challenges for the future. One that is really coming together now, already, or just more is the bringing together not just of vision, but sound, text, video. And already we're getting that thing. You don't just put in a prompt of text. You can take a picture, prompt it on what you see. And I think this will get more and more. You see it as human beings. We exist not in a world of just text and language, but all of the senses. We'll integrate all those senses together, and our AIs will be more integrated objects than just language. But the scary thing is, probably it's just a matter of time. We will achieve all of these things eventually. And I think most of the discussions is not whether it's possible, but just how long. That, thank you very much.
Wonderful talk, and we have plenty of time for questions. So, please.
So the question that always comes up when we hear about this is, do you think there's anything that we have to be afraid of?
Interesting. Mostly I always say no to that because my mindset is normally in the space of what's happening in the next 5 years. So I will answer it with not in the next 5 years. But the reason why I'm pausing is because, you know, when I was preparing this talk and thinking about writing the slide about the future, and I say it's a matter of time, it does seem that there will become a point, inevitably, where AI will get better and better and better. How we as human beings organize society to cope with that in the far future is a challenge. The optimistic side says we had that challenge with nuclear weapons, and thus far we've passed it. We've had the challenge now with climate change, may or may not. But we tend to identify the challenges. So I'm going to say there is a challenge coming in the future. But I will put it in the far future and hope we can.
Well, I have another optimistic possible future outcome, and I wanted to know what your thoughts were, is that we become androids, essentially merging with AI.
Okay, I would say I don't want to suddenly become a Cyberman. What I would say is, and actually I realized after I gave the first answer, I wanted to say something else, which is a bit related to your comment. There's another risk, which is that we don't embrace it and then don't solve the problems that challenge humanity in terms of climate change, energy, illness. So it could go exactly the opposite way. You have a risk of passing an opportunity to solve a huge number of problems. So, you know, opportunities are there. With every opportunity, there's also.
Hi, I just want to ask, just considering the two different terms, machine learning and AI, at least like me as a researcher, I'm using machine learning all the time. If you're doing a linear regression, we call that machine learning. Calling it AI is a bit optimistic. And I wonder if, I guess it harms a science communication point of view, should we differentiate those terms better? One as a tool and one as more of the leaning towards what we now see as going more towards a general AI point of view. Should those terms be differentiated more?
Interesting. When I was in academia, most people always spoke about ML. When I went into industry, everyone spoke about artificial intelligence. I don't know how much words matter. I think artificial intelligence just has a connotation to it of intelligence. Machine learning has a much more modest set of goals and ideas. And so a lot depends on what you're going to sell and to who.
So I'm really curious. My understanding is that it's predictive. So what's the next most likely word that'll come up in a large language model? So how far away are we from actually, or how do they structure it so it's actually doing the reasoning? Like I read, like Q-star might be doing it, they don't know. And then if I may, if you'll indulge me, I'd also love to know how AI is going to affect quantum computing and vice versa. And I don't know if I'm allowed this much, but what is ChatGPT doing compared to Anthropic? How are they training their models differently?
Great thing about the fact you've asked me 3 questions, I can probably answer 2, and by the time we've done, you'll forget them. So we'll see where we get. So I've even forgotten the first one myself. So the first thing was about the difference between reasoning and the predictive thing in language. This is exactly the point where I say careful analytic, because it is built on statistics. So it does something that's very persuasive to a human being chatting. But if you run it through maths, and they will doing some very other things, but every now and again you get something in no mathematics, state no mathematics. It can be very successful, but then equally weirdly wrong. That's because it's been written as this language model. So indeed, people like OpenAI and Anthropic may well be working on ways in which you do that reasoning better. And I am not in the secret know of what Q-star is doing. Please contact me if you're watching. Obviously, this was the reason I put it up there. That is the challenge. It may be well tied to it. The people in OpenAI and the other large language model people, they know this. So the ways in which people are trying to get around it differ. And you could talk for an hour just on that. They're my chance. Yes.
So similarly to how thermodynamics was developed in order to explain things that people were designing and building at the time, do you anticipate the emergence of a theory that explains these complicated entropic processes, the unjumbling of the noise, so like self-assembly, artificial intelligence that's like robust enough that makes it more understandable and applicable in a wide set of circumstances?
Yeah.
What time frame do you think that's going to come out?
Time frames are hard, but yes, I do anticipate. Oh, sorry. So the question was, I paraphrase slightly, do we think we will, just as in thermodynamics, we had a theory that we built to explain machines of the Industrial Revolution. Are we going to have a theory of AI that explains all of the complexities? And so I would say yes. And that's what we're doing here this week. Because as scientists, we want to explain stuff, and we will work hard. And I can already see many successes explaining different points of view, how AI works in different ways. I don't think we're completely there yet, but we've made important stepping stones in the right direction. And the timeframes we've been studying this have not been that long, let's say physics. So yeah, when they write history of science, there'll be this amazing thing where people in industry got lucky. You're very lucky. They're very clever people. They did brilliant jobs, and they beat the academics what they achieved. And we are now going to study what they've done, and I think we will have a good theory explaining how it works.
Could you elaborate on what you wrote about the magnet?
Okay. You're gonna do a whole slide on that? And I was like, no, I'll try and do that quickly. See if we get there. How magnets work is you've got what are called domains. Domains can, they're like little magnets inside. But they're only little. And they're all, say this is north and this is south. I've got loads of them everywhere. Now, if the whole material is not magnetic, then they all point in the overall magnetization, so it cancels out. You then make a magnet by aligning them all, direction, because they're all pointing the same way, you get a magnet. Okay? Now, what makes them align in the same way? Because two nearby domains actually have got some interaction which pulls them together, or opposite, or something. The result is you get a probability of whether things are sort of up or which way these things are pointing. That probability depends on how strong the interaction is between the nearby domains. I noticed I said probability. A lot of the things that you always want to learn in AI are probability distributions. What Geoffrey Hinton did, something called Boltzmann, is say I could just learn the different ways in which domains interact. It will never happen in physics. You tune them so that the probability, how the domains are going, reproduces some really complex probability distribution, like numbers on a page. He did it. So it's a ridiculous thing. When you're training, it's like training a substance. It's like a magnet whose interaction between domains changes, pick it just the right thing, reproduce a really complex probability. Second.
Where did the name of artificial intelligence come from, and who named it? Did they copyright it, or and do you think it will stay with? Where did it come from then? What does it mean?
See, there's always one question, can't I? Michael, where did it come?
It was actually some people had just come up with a computer programs that prove theorems, and they said, "Wow, you know, this is the computer could do all these things people could do." And John McCarthy coined this name for it.
1956. Very interesting. Yeah.
A little bit about the evolution of the model or the tool that AI is using to go from the high entropy to the low entropy.
Oh, God.
Yeah, I can add like my construct of how it's
Okay, so the
moment in time that
yeah.
became frozen.
So the question was, I skirted over the process by which the AI learns to reverse this diffusion process. Because you're right, that's very hard to do. No, let me tell you a secret. Whatever you give any public talk, what you're always doing is the following thing. There are pages and pages of mathematics. And then you go, I turn the pages of mathematics to something which is an image and things where my hands somehow will be involved. And a lot of the time that works. Every now and again, there's a bit where you go, I could write an equation, but then I go, how do I do more? And maybe it's the failure of my own intuition on this problem. I'm going to be honest, I have a hard way to say how that is really going to learn. So you could write down equations for that. I can't give you an intuitive answer. I apologize. Maybe other people in this audience who can. And then pressure afterwards and tell. But no, I'm going to bail out. But I think it's important to realize underneath all of this stuff, when you do science, there are equations you write down that are solid, which underpins everything. And then there are the concepts which have inspired the equations, but sometimes you can't always go the way. Oh, sorry, am I?
In reversing the diffusion process, you can't get the exact gap.
Okay. The question was, in reversing the diffusion process, how do we get the exact? And this is an important point. You don't get the exact. I learn it from taking, say, 100,000 cats, fuse them all down, and then the reverse process. But because the noise will never be the same that you start with, you don't end up with the same cat. So this is the great thing. You generate things you've never seen before, and it's never seen before. Based on, it understands how to go from a whole load of cats into randomness, then reverse it. And you start with a random thing that's not ever the random thing that you ended up with from one of the exact cats. You'll generate a cat, but it's not a cat that's ever been seen. Oh, if you know exactly the starting point, but that's not the point. The point is, to generate something you've not seen before. Now, Michael, you judge because you've been waiting a while. Sorry.
So in a sense, it actually connects to his question. If we all agree that it's a cat, and let's say that's fact,
Yeah.
how will AI, as it gets better, handle alternate facts?
Ooh, I like that question. So I think
Can you repeat that?
repeat the question. How will AI, as it gets better, handle alternative facts? So what you're describing there is you can define this process. It's really learned to do with cats. And then, but how am I going to generate a dog? You can't, because if I've not shown it what a dog ever looks like, done the same trick, it can't do it. So there's a very interesting thing here, which is when we generate stuff, we tend to generate things built around things that we've already seen. But in the end, isn't that what I've done? When I generated all of these ideas, well, when humanity generated all these ideas around AI, we were using what we'd seen before, just maybe tweaking it a bit, applying it in a different way, whatever. True creativity, where you create things that you've never seen and not like anything before, is exceedingly hard, humans and AI. So I'm not going to tell you that we could do that with AI. I don't think any humans can do that either. There's always a stepping stone to connect with what's gone before.
I listened to a lecture by Yuval Harari talking about we provide AI with all this data from our phones to the point that it can know us better than we know ourselves and can manipulate us. Not necessarily for good or bad, but probably for profit. What's your thinking on
I've got to repeat the question. So I will paraphrase to Yuval Harari has said that data has been constantly collected from us, the phones, maybe other things. And this can be used for profit, certainly not necessarily is the concept. That's true. We're back to the question that came earlier about there are challenges whenever we have opportunity. Now, I think a lot of this is going to be about education. We will learn to become more knowledgeable about and protect our own data. Data will be seen as something of value, something you buy, sell, allow, give permission to, or not. Well, in principle, a lot of that's true, but very few of us think of it in the same way that our children will in post-AI side. So yes, technology comes societal change and cultural change. And I think that notion of our data will be one of those things.
I was going off this alt data, that whole idea of garbage in, garbage out. And there is so much garbage out there on the internet, which we all know not to be true, but perhaps a computer isn't discerning that. Where is it picking the good data from the bad data and reproducing that?
So a key point is that these models are not learning unguided. The companies that make these large language models carefully curate data they give it because they know exactly what will happen if they don't. And there were some notable blunders that happened. And for example, a language model very early on was trained on Twitter, And they were surprised that it was a racist. So very rapidly, people realized that to get the control you have of the model is the data you feed it. And how you curate something when the amount of data is so huge that you can't sit there by hand sifting it, means you end up making models that sift through than it used to train a model. But so you can always find a little hole there somewhere. But these companies are being really quite careful. Their success has been because they curated that data very well.
One last question.
Yes, thank you. My question is, since human beings are simply intelligence embodied in an organic form, and AI is intelligence embodied in an inorganic form, will there be a point of synthesis where we'll see concepts like rights and justice applied to AI technologies?
And there was already a case in Google Brain. Somebody tried to give the AI rights. What do I say to them? The problem is this is being recorded. And in the future, AI may recognize that I did not support it. So I, for one, are all in favor of giving AI rights. And in the future, please remember that I said that.